We were discussing earlier about the stability of floating bodies and we will continue with that. So if you recall the sketch which we were discussing in the previous class, we identified a point known as metacenter, and the motivation behind identifying this point is that when it is a floating body and it gets displaced and its submerged portion within the water changes its configuration, the center of buoyancy does not remain fixed at its own position. So referring to a fixed center of buoyancy might not work as a stability criterion. Now we will try to find out, as what we have done for the case of totally submerged bodies, that how we can find out a stability criterion for floating bodies. As you can see, the presence of or the existence of this metacenter is something which is equivalent to the presence or existence of the center of buoyancy for a case when the center of buoyancy remains at its own position. So the metacenter somehow reflects the location of the center of buoyancy with respect to the axis of symmetry of the body. So it has some relationship with the center of buoyancy definitely, but by specifying the metacenter or by specifying the center of buoyancy just as their absolute locations, it is not just possible to talk about the stability criterion. So we have to look into more details. To look into more details, we will set up some coordinate axis. Say we have x axis like this, say we have z axis like this, and the y axis is perpendicular to the plane of the figure. So the y axis is this dotted line which represents an axis in the other view. Now if we consider that how we calculate the submerged volume, the volume of the solid which is there within the fluid. Let us say that at a distance of x we take a small element of width dx, and this element has a depth of z. So this element, if you look into the other view, will be like this, which is basically located at a distance x from the y axis. Let us say that this shaded area is dA. So you can say that z into dA is a representation of the elemental volume of this shaded portion. Now when it is tilted, even when it is tilted, we fix the x and z axis with respect to the body and we keep them as same. So we still have this as the x axis and maybe this as the z axis. These are fixed relative to the body. So although the body has tilted, we are using a body fitted set of axes, so to say. Now let us say that the angle of tilt is theta. If the angle of tilt is theta, then what happens? We can find out that what is now the displaced volume. So if you consider again, say at a distance x from here, some strip of width dx. Now if you consider the displaced volume is of course corresponding to this part is like z, same as this one, because it is the same axis that has got tilted. So if this is z, this displaced part is also z, but you have the additional displaced part which maybe let us mark with a different color. So this is an additional displaced volume. So this additional displaced part will correspond to a particular length along the z axis, and what is this? Remember that if this angle is theta, then the angle of tilt of the x axis with respect to the horizontal is also theta. So what is this dimension? You know that this is x, so that is x tan theta. So if we calculate what is the displacement in centroid of the displaced volume, that is what is the difference between the x coordinate of say the original center of buoyancy, let us give it a name, that there was an original center of buoyancy say CB, and now the new center of buoyancy is CB prime. So the difference in x coordinate of CB prime and CB, that is what we are interested to find out. What is that? Center of buoyancy you can calculate by utilizing the formula for centroid of a volume, which is here the displaced volume. So this will be integral of x dV. So x is this x, what is dV? So you have this total height as x tan theta plus z dA. dA is the other area in the other view. So the depth times the dA is the volume. So this divided by the volume of the immersed part. Because of the symmetry, the volume of the immersed, total immersed volume does not change, whatever comes down the same volume goes up above the water. So the total displaced volume does not change, minus what was the original one, integral of x z dA divided by V. It may be easier if we mark the original CB and the displaced CB here. So there has been a displacement from CB to CB prime, the location of the center of buoyancy has got shifted. So this is nothing but equal to CB prime, that is the length that we are talking about, and this is equal to integral of x square tan theta dA divided by V. Theta being like a constant parameter, tan theta you can take out of the integral, and this area integral is carried out over the shaded area dA. So what does it represent if you take tan theta out of the integral? Second moment of area with respect to which axis? No, with respect to, you see it's, you refer to now this plan view, integral of x square dA is the second moment of area with respect to the y axis. So it is tan theta into Iyy by V, where what is Iyy? It is integral of x square dA. Now referring to this figure, you can say that for a small angle theta, CB prime, this particular small distance is a small arc of maybe a circle. So you can write this as approximately CB m into theta for small theta. It is just like S equal to r theta for a small part of an arc of a circle. Because this is very small, we are assuming a small displacement, we test stability not with a large displacement but with a small displacement. And metacenter, M is the metacenter. Now for the same smallness tan theta will be approximately equal to theta. Of course you are expressing theta in radian, that is understood implicitly. So then if you equate the two parts, what you will get, CBM is equal to IYY by V. Now look into this figure. In this figure you see that M is above G. When M is above G, the couple moment created by the forces is trying to restore the body to its original configuration. However, if G was above M, it would have been just the opposite case, that you can clearly visualize. So what is important here is the location of M relative to G, just like for a totally submerged body it was location of B relative to, or the center of buoyancy relative to G. So what we are interested to find out is what is the height Gm. So Gm you can write it as CBM minus CBG. So IYY by V minus CBG. See why we have written the formula in this way. In the right hand side you have terms which are independent of the deformed configuration or deflected configuration. So if you see here IYY V, these can be calculated based on what is the original configuration, and CB is the location of the original center of buoyancy relative to the body, G is the location of the center of gravity relative to the body, and the distance between those two, that does not change with deflection. So we are able to express something which should be a function of deflection in terms of certain things which are not functions of deflection. Therefore this is also not a function of deflection, and M remains sort of fixed, but you have to keep in mind that there are certain assumptions that go behind this. What are the important assumptions? Theta is small. So this analysis is valid only when you are having a small theta. Not only that, we have implicitly assumed that the z axis is an axis of symmetry for calculating or for coming up with this expression. So we are essentially dealing with a simplified case with symmetric bodies, that we have to also keep in mind. Let us look into an example where we illustrate the use of this expression for finding out the stability criteria. So what is the stability criteria here? Let us summarize. If M is above G, it is stable. If M is below G, it is unstable, and obviously if M coincides with G, it is neutral. So you can clearly understand that M plays the role of equivalent role of center of buoyancy in this case, but it is not exactly the center of buoyancy. We consider a very simple example and we will illustrate the use of this through that example. Let us say that you have a body of this shape, rectangular parallelepiped shape, and you can give dimensions, say let us say A, maybe this is B, and let us say this is C. Say this is partially immersed in a fluid, so it is like a floating body. Okay. Now let us try to see that how we can apply this stability criterion here and what are the important issues. First important issue is that when you apply this criteria, what should be the y axis with respect to which you are considering the second moment of area. If you look into this problem very critically, you will see that there are certain non trivial issues, like you can consider maybe this as one of the frontal surfaces, you might consider this as one of the frontal surfaces and even the third one. So accordingly it is not very straightforward to say. So when we drew the picture of the boat, see it could be this front part, it could be the side part, both are exposed to the water, I mean both are within the water. So if you could say that what should be the corresponding axis that you need to consider, or does the choice of the axis change if you shift your attention from the frontal area to the side area. At the end what you are bothered with, you are bothered with the plan view. So when you have the plan view, which is like the top view of this one, what is the plan view? It is the intersection of the body with the free water surface or free fluid surface. So that particular view, it boils down to the same when you consider this surface or this surface, but again when you look from the side and when you look from this one, maybe in one case you are considering this as the y axis, in another case you are considering this as the y axis, both axes are relative to the top view. So question is with respect to which axis you should evaluate this. See this is what, this is like evaluation of a safety criterion that it will be stable. So when you want that it should be stable, what should be the guideline? The guideline should be that like you want this to be positive, right, that means this height is greater than this height, then like m is above g. So this, the way in which this is written, the right hand side has to be positive. So more positive means, so to say, it is like it is more stable, so to say. So if we take the least of this one, least possible value of this one and still find that the right hand side is positive, then for all other cases it should be positive. So it is like a safety design. So you look into the most adverse condition, make sure that it is positive even for that. So for better conditions it would always be better. So out of these two axes, for one axis it will be, what will be the I? It will be b a cube by 12, another will be a b cube by 12. So you take the smaller one, that means if b is smaller than a, as an example you take this one. So then when you substitute that in this expression and still you calculate this as positive, you are assured that it is safe, because with respect to other axes when you calculate the metacentric height it will definitely be greater. This is known as metacentric height. And really when you calculate different metacentric heights based on different views, these represent different types of angular motions like rolling, pitching, these are different technical names based on with respect to what type of axis it is tilting. So but just for design, simple design, you can consider the smaller one and you divide it by the volume, not the total volume but the volume of the submerged part, so that you can easily calculate based on what part is submerged. Let us say that d is the submerged depth. It is easy to calculate this because you can use the equilibrium, that for equilibrium the buoyancy force must be equal to the weight. So from that, if you know the density of the fluid and density of the solid body, you can come up with what should be the equilibrium d just by very simple equating of the two forces. So you can calculate what is the volume which is immersed in the fluid. Center of buoyancy location you can get from the centroid of the displaced volume. Center of gravity also has a fixed position with respect to the body. So you can clearly substitute these dimensions and find out what is the metacentric height. So this effectively requires only the calculation of the immersed volume, the calculation of the second moment of area with respect to these axes, and specification of the locations of the center of buoyancy and center of gravity with respect to the axis fixed on the body. So that is a sufficient information to calculate the metacentric height. So what we can clearly see is that if m is above g, that makes it stable. That means lower the location of the center of gravity, it is having a greater chance that it would be stable, because then it is a greater chance that m is above g, lower the location of g. So location of g, if it goes higher and higher, it might make a previously stable system or convert it into an unstable one. Let us look into an animated example to consider this case. So in this animated example, what we will see that how the stability may be disturbed because of the shifting of the distribution of weight of the body. So let just look into it carefully. So there is a body which is given a slight displacement, and you will see that for small displacement it oscillates like a pendulum. We may easily derive what is the time period of that. Now you see that the distribution of the weight is being altered, so the center of gravity is being shifted higher and higher by putting the load more and more towards the top, and you see that it topples. So obviously this is a clear illustration of this concept that we have learnt in this example, that if you have metacenter above the center of gravity, it makes it more stable, and otherwise it is not so. So now for small oscillations you could see that it or for small deflection you could see that it oscillates like a pendulum. So when it oscillates like a pendulum, it has a time period, and that may be calculated by calculating the moment of the resultant force with respect to the axis. So if you have a tilted axis like this, and if you have a force Fb, which is the buoyancy force, this force has a moment with respect to the axis of the body. So what is the moment of this force with respect to the axis of the body? You can just find out the perpendicular distance of this force from the axis of the body. Okay. So it will be just, what will be the perpendicular distance of this buoyancy force, line of action of the buoyancy force? I mean, you can see that it eventually passes through the axis of the body, right. So it is not this force individually which is important, it is the couple moment that you are having, the so called the restoring couple. So you have also the W, and it is basically the couple moment of these forces that you need to consider. So the perpendicular distance between these two. In terms of the metacentric height, could you express this? So if you have this as the metacenter m, so we are interested about this distance. So it's possible to express it in terms of the metacentric height. So this angle being theta, it is, what is this perpendicular distance? Gm sin theta. So the moment of this force is W Gm sin theta. And the resultant moment of all the forces is nothing but, if it is like rotation of a rigid body with respect to a fixed axis, it is a restoring moment. So you should have a minus sign associated with 1. That means whatever is the chosen positive direction of theta, theta dot, theta double dot, this has a direction opposite to that to bring it to its original configuration. So you can write this as, so I is what now? I is the mass moment of inertia, it is not the same I that we were talking about, it is the real mass moment of inertia with respect to the axis of the body relative to which it is tilting. So this plus, for small theta again this is approximately equal to theta, that is equal to 0. So it is just like equation of a spring mass system, mx double dot plus kx equal to 0. So what is the natural frequency of oscillation of this system? Root over equivalent stiffness by equivalent mass. So W into Gm divided by I, that is the natural frequency of oscillation of the system. It is an angular oscillation, not a linear one. So you can clearly see that greater the metacentric height, greater will be the frequency of oscillation. So if it is a ship, it will be more uncomfortable to the passenger. So these are two conflicting designs. See, greater the metacentric height, you expect it to be a safe in terms of stability, but it will have more oscillation within that stability regime. That means for a passenger it may be quite uncomfortable. At the same time, if it is for a used for a particular say critical purpose like warfare and so on, so their stability of the ship is more important than the comfort of the crew, and there obviously it is the stability that should be the driving factor for design. So when a ship is designed, you have two conflicting things, one is the comfort, another is the stability, and comfort factor comes from this high frequency of oscillation, and the stability comes from the metacentric height or location of the metacenter relative to the center of gravity.